Welcome to the UGC lecture series. This is the PG Pathashala lecture on data structures. In this module and the next module, we are going to cover the analysis and design of algorithms, a very short introduction to these two topics. You have another course on design analysis of algorithms as such. So, these are the people who are contributing to this module. So, let us look at first the learning objectives. The learning objectives of these modules are to understand the concepts of algorithms, to appreciate the need for the analysis of algorithms, to know about the analysis of algorithms using the big O notations, the famous big O notation, to understand analysis using recurrence equations. We are going to only a very small peep into recurrence equations. The keywords associated with this module are analysis, running time, best, worst and average case analysis and recurrence. Now, so before we go forward, let us look at what is an algorithm. So, what is an algorithm? It is a clearly specified set of simple instructions to be followed to solve a problem. Algorithms have always been associated with computer science, but even a sequence of steps that we do to achieve a certain task can also be called as an algorithm. Like it takes a set of inputs, values as input and produces a value of set of values as output, and basically it does a mapping from input to output. Any algorithm tries to do a mapping from input to output. So, what are some of the properties of algorithms? That is the next question that we have to ask. So, not everything that you write in a sequence of steps can be called algorithms. So, algorithms, first it must be correct, that means it must compute the proper function, only then you call it a algorithm. It is not a trial and error. It must be composed of a series of concrete steps. That means, now we are going to we are talking about the algorithm associated with computer science or computing. So, it must be composed of a series of concrete steps. What is the meaning of concrete steps? Concrete steps, that is, each of the steps should be executable by a machine, whichever is the machine you consider. Then there can be no ambiguity as to which step will be performed next. It should be clearly specified. If such a condition, this step will be executed, and if this is a step, this is a step that will be performed next. And it must be composed of a finite number of steps, that is, you should not have an algorithm, you do not say it is an algorithm if the number of steps is infinite. So, it has to be, that means it should be completed in a finite number of steps and it must terminate. So, there is no question of it going into an, as I already told you, into an infinite loop. We frequently interchange the use of algorithm and program, but actually they are not the same. Program is different, algorithm is different. We will understand that as we go along. Now, let us again continue about algorithm analysis. Up to now we spoke about what is an algorithm and some of its characteristics. Now, we go directly into algorithm analysis. What is algorithm analysis? Algorithm analysis is a process of determining the resources required when executing an algorithm. Please note, we are not telling executing a program, we are talking about executing an algorithm. So, when we say determining the resources should be generic. So, what are the resources that are normally considered? Memory required, what is the communication bandwidth and what is the computational time. Usually, the computational time is considered as the most important resource that we have to analyze and determine how much we need. So, running time of an algorithm is almost always independent of the programming language. So, here when we talk about analysis of algorithms, we do not consider any programming language. It is almost always independent of the programming language. We will see as we go along what it is actually dependent on. Now, before we go further, let us look at what is the purpose of algorithm analysis. Why should we do this? Why should we know what are the resources? There are a number of reasons why we should do algorithm analysis. So, one is to estimate how long a program will run, how much time will it take, that is an obvious purpose of an algorithm analysis. And then to determine the largest input that can be reasonably run, that can reasonably given to the program or run using the program. The idea is that depending on your algorithm, you should not it should not get stuck, it should not have some problem because the number of the input size is too large. So, sort of by doing this algorithm analysis, you can determine or estimate, you cannot determine, you can estimate the largest input that is possible for this particular program. Then to learn how to analyze an algorithm's running, without actually coding it. So, you are just going to look at the steps and then you can sort of simulate it and understand how the algorithm is going to work and analyze it without actually coding it. Normally, if you want to determine the running time, you have to code it using a programming language and run it on a system, and that is not independent, depends on the speed of the system and things like that. So, here without doing any of this, we are getting an estimate or estimate of the running time or analyzing the algorithm without coding it. Then of course, another obvious reason why we should do algorithm analysis is to compare two different algorithms for doing the same task, the efficiency in terms of running time. Then sometimes you also do analysis to focus on parts of the code that takes the largest number of or is executed the largest number of times. When you are writing a new program, a new algorithm to do some task, then if you do the analysis appropriately, you can find out which component of that particular algorithm is taking the largest chunk of your running time, okay, or the largest number of times it is executed. And you also do algorithm analysis to decide on the algorithm for a particular application. So, depending upon what the algorithm running time is dependent upon and the application, you can choose to match the two. Now, let us go directly to algorithmic performance. There are two aspects of algorithmic performance. One is time, basic two, one is time and one is space. So, time means the instructions take time, any instruction that you have to execute takes time. So, how fast does the algorithm perform? What affects its runtime? So, if you take a runtime, there are certain components of the algorithm which will affect the runtime more than others. So, what is it that affects the runtime? So, that is the first important aspect of algorithmic performance. Obviously, the second important part is the space. So, data structures that are used to represent the data and manipulate it require space. So, what are the types of data structures that are used, and an important, very important aspect is how does the choice of the data structure affect the runtime. Now, we are more bothered about this aspect in this course, okay, because when you talk in general about design analysis of algorithms, we are not we are bothered more about the time and the run and the space, but here we are actually talking about this algorithm analysis and design because data structures also plays a very important part in determining this runtime. So, if a data structure you choose is say array or you choose a linked list, the way the running time and the algorithmic component and the number of times it is executed, everything changes. So, that is why data in a course on data structures you should have a small idea of what is analysis of algorithms as well as the design of algorithms. So, in algorithmic analysis basically we focus on the time aspect only. So, how to estimate the time required for an algorithm and how to reduce the time that is required, how to estimate it and how to reduce it. So, what are the factors that affect running time? So, that is the next question. The factors that affect the running time are the computer that you use, the compiler that you use, the algorithm that you use, and very, very importantly, what is the input to the algorithm. So, certain normally when you do algorithm analysis theoretically, we do not consider the computer, we do not consider the compiler, we consider the algorithm used and the input that is taken by the algorithm. So, and machine model assumed, we assume a machine model, we do not actually take a machine and do anything, we assume a machine model, we assume that instructions are executed one after the other and we do not assume that there are any concurrent operations occurring. When we do algorithm analysis, this is an assumption we make which is called the machine model assumption. We assume that the instructions are executed one by one sequentially, no concurrent, that is no parallel operations is assumed, because if you do that the time required will change. Okay. Now, let us take an example. This is a naive approach, that means what is the meaning of naive approach? We do not consider anything, we just do a brute force approach, we will come to brute force later. So, list all paths between a given pair of points. So, suppose you want to find, here we are trying to find the shortest path between two nodes assuming a graph. So, the number of nodes is n, the number of paths is e. So, you just list all the paths between two given points and compute the travel time between each point, and then whichever gives you the shortest travelling time, that is the shortest path. So, there are too many parts actually. So, the number of parts will be n factorial approximately equal to n by e to the power of n, which means it is very large. So, if you assume it will be impossible to run your algorithm even for a value of n is equal to 30. So, there is a need, what we are trying to say here is this is a naive algorithm, and if you use this naive algorithm your running time is just going to explode, and so there is a need to compare two algorithms and decide for particular problems and tasks and particular things what is the algorithm you have to choose. So, that is the incentive for designing efficient algorithms. Now, let us take another example which is called the selection problem. Given a list of n numbers, you have to determine the largest where k is less than or equal to the kth largest number where k is less than or equal to n. So, the first algorithm that we can do is read the n numbers into an array, okay. Then sort the array in decreasing order by some simple sorting algorithm. We have not gone into sorting algorithm. So, some of you may have studied it in a basic course on data structures. So, sort the array in decreasing order using some simple algorithm and return the element which is in position k, because whatever is in position k, that will be the kth largest, okay. Not the largest, we are looking at the kth largest. So, this is a algorithm 1. Another algorithm that can do the same task. What is the task? Finding the kth largest number in a list of n numbers where k is less than or equal to n, okay. Read the first k elements into an array and sort them in decreasing order, okay. So, each remaining element is read one by one. If smaller than kth, then it is ignored. If it is larger, it is placed in the correct spot in the array, bumping one element out of the array. The element in the kth position is returned at the answer. The idea here is that you are doing an look at the logic of the algorithm. What you are doing is, suppose let us assume n is 100 and k is equal to 20. So, you read the first 20 elements, you may not have the largest there, okay, remember. You want the 20th largest. So, read the first 20 and sorted them in decreasing order. So, you will sort them, then you take each and every your 80 remaining elements, you read them one by one. If it is smaller than k, then obviously the kth element, then obviously it does not need to come into this. So, ignore it. Otherwise, if it is smaller than k, you place that in the correct place and bump out one element after the other. So, at the end of the algorithm, whatever is there in the last position, the kth position or the 20th position will be your correct element. Okay. So, that is what is this algorithm. This is slightly different from the previous brute force method. So, which is a better algorithm? Just put the value for n. When n is equal to 100 and k is equal to 100, which is the better algorithm. When n is equal to 100 and k is equal to 1, which is the better algorithm. So, just think about the steps and look at this. I am not going to discuss this. The idea that we are trying to tell here is it depends upon the values that you give to the algorithm. So, depending upon whether n is very large or k is nearer n, k is nearer to 1, the algorithm time required changes. So, that is one aspect we are trying to tell through this example. So, what happens when n is equal to 10 lakhs or when k is equal to 5 lakhs. So, that is very different from what n is equal to 100 and k is equal to 100. So, this is what we are trying to tell here. So, there are many other better algorithms to solve the problem that we were spoken about, maybe you can look them up. Now, let us go to, so what we were trying to tell till here is that running time is the important part in the analysis of an algorithm, and at the same time the running time depends on a number of factors, the compiler, the computer that you use, the number of the algorithm that you use and the size of the data you use. This algorithm that you use and the size that you use have a big relationship, that which is shown by the selection algorithm, selection problem, where depending on the algorithm you use and the size of the data and even the size of the, you want to find the kth element, the size of k, the algorithm's efficiency is different, or the running time, let us not say running time is different. So, this is another important aspect that we have to talk about, which we will discuss later again. Now, time complexity is basically called as a function, okay. Specifies how the running time depends on the size of the input. So, basically we are saying that the running time of an algorithm depends on the size of the input. So, it is a function mapping the size of the input to the time, that is time is t of n, where n is the size. So, what is the definition of time is the next question you will have. How do I define time? So, define time can be seconds, which means it is a machine implementation dependent time, or it can be the lines of code executed, or it can be the number of times a specific operation is done, addition for example. So, you can define time in different ways. Normally, the number of seconds is never used because each machine has its own idiosyncrasies and people across. So, you cannot compare. So, machine dependent type of time like seconds we never use. It can be the lines of code sometimes used, but basically it is based on the number of times a specific operation is performed. So, there are bounds for the algorithms, not the programs. Programs are just implementation of an algorithm, and almost always the details of the program do not actually affect the bounds fixed for the algorithm. So, that is what we do, and bounds okay. So, as I already told, bounds are for algorithms. So, a problem can be solved with several algorithms, some are more efficient than the other. That is the main reason why we are talking about algorithm analysis, especially when the data is very huge. Your efficiency of the algorithm you select very much determines the efficiency of your application also. So, what is the meaning of efficiency of an algorithm? That is the next question. So, it is a runtime in the computer, then it is machine dependent. So, machine independent analysis is what we want, as I already told you. So, here we go to the next step in algorithm analysis. We assume that every basic again we are making an assumption. So, there are many assumptions we make. We make an assumption it is a machine model where concurrency is not allowed, one step after the other is implemented. We do not consider the compiler, we do not consider the computer, we only look at the operations that are implemented, not even the lines of code. Now, what we are saying, we assume that basic operation whatever it may be takes constant time. What are basic operation? Examples of basic operations are addition, subtraction, multiplication, memory access, accessing a particular variable value stored in the memory, and there are some non-basic operations like search, sorting and searching. We will come to this later. So, efficiency of an algorithm is the number of basic operations it performs. So, what we are going to do? Now, we have come very specifically, we are saying that we are going to talk about algorithms in terms of the number of basic operations that it does. We do not distinguish between the basic operation, we do not distinguish whether it is multiplication, division, accessing a memory, all are considered. This is another assumption we are making, that all the basic operations will take constant time. So, the theoretical analysis, so that is why we say it is only a theoretical analysis. Theoretical analysis of time efficiency is analyzed by determining the number of repetitions of the basic operation as a function of input size. Now, when we started off, we said that we are only bothered about the input size, how it affects the efficiency or running time of an algorithm. Now, what we are trying to say a little more detail, we are saying the number of repetitions of the basic operation. Remember, all basic operations are assumed to take place in constant time. So, the number of repetitions of the basic operations, which will be a function of the input size. So, basic operation, as we have already defined, is the operation that contributes the most towards the running time of an algorithm. So, different basic operation may cost differently, but for the initial stages we can assume that they all take constant, cost the constant. So, time complexity you can define in this way. Let us assume the input size is n, then T of n, that is the time function time in terms of the input size n, which is called the running time, is approximately equal to C op into Cn, where C op is the execution time for basic operation, any basic operation, and C of n is the number of times the basic operation is executed. So, you have T of n is equal to C of op, that is the time taken for a basic operation. We are assuming the time taken for all basic operations irrespective of the type is the constant, and C of n is the number of times those basic operations are executed. So, let us take an example and explain this. Let us say we have a problem, you want to search for a key in a list of n items. The input size measure would be the number of items in the list n, and the basic operation there will be the key comparison between two of the keys. Multiply two matrices of floating point numbers, the dimension of the matrix would be a good measure, and the floating point multiplication would be a basic operation. Compute a of n, a to the power of n would be the input size and floating point multiplication again would be the basic operation. Let us take a typical graph problem. it would be the number of vertices, and you can take the number of edges also, or you can not take the number of edges. So, visiting a vertex or traversing an edge would be the basic operation. So, the basic operations that we are talking about can be defined in terms of the problem that we have and the input size measure, that also can depends on the problem that we have. This is some examples, input size and the basic operation examples. To do these operations, we need to do some other addition, multiplication, so on, that we have not looked at here. So, what is the efficiency of an algorithm again? In fact, we will not worry about the exact values, but we look at the broad classes of values or the growth rates. Now, when we talk about the efficiency T of n, that is the running time, we are not going to talk about exact values at all. Okay, again an assumption, we are not going to talk about exact values, we are going to talk about a broad class of values which is called as growth rates. So, let there be n inputs. Okay. If an algorithm needs n basic operations with another needs 2n basic operations, we will consider them to be the same efficiency category. So, whether it is n, 2n, 3n, everything comes under the same broad category, we are not differentiating it. However, we distinguish it between exponential of n, n log n, that we differentiate, but we do not differentiate between whether it is 2 into exponential of n or whether it is 5n, that we do not distinguish. We distinguish in terms of the functions that n can take. So, that with that we come to the asymptotic algorithm analysis. Okay, what is this asymptotic analysis of an algorithm? It determines the running time in terms of something called a big O notation. We will come into that. To perform asymptotic analysis, we find the worst case number of primitive operation executed as a function of the input size, and we express this function with the big O notation. Now, I have not told you what is this worst case, best case and average case. We will come into that later, but in essence what it means is worst case, what can the worst be for that particular algorithm, whatever may be the input size and whatever may be the other parameters, what can be the worst. So, that worst case number of primitive operations that is required to be executed as a function of the input size, if you take that, we express this function in terms of the big O notation. Since here constant factors, lower order terms are eventually dropped anyhow, so we can disregard them when counting the basic operations. When we count the basic operations, does not matter, lot of things does not matter, because we are not bothered by this whether it is of the order of n, we are not bothered whether it is of the order of 5n, 10n and so on. So, now let us look at asymptotic growth rate. There are 3 types of asymptotic growth rate, a way of comparing functions that ignores constant factors and small input sizes. Of the order of g of n, the class of functions f of n that grow no faster than g of n. This is called the big O notation, that is it is a class of functions of some f of n. It cannot grow larger than g of n, then we call that as big O notation. If it is the same rate of g of n, then we call it as the big theta notation, and if it grows at least as fast as g of n, it is called the big omega. It is just a question of how you define that order. So, we normally consider the big O notation, where we say that it can grow no faster than g of n. Okay. So, that is what. So, just remember no faster, at the same rate, at least as fast as. We consider grows no. So, once you find out the order, you know that it cannot go beyond that. So, this asymptotic notation of the big O is written as function of n is of the order of g of n. There are positive constants c and n o such that f of n is equal to c of g of n, where n capital N is greater than or equal to n 0. The growth of rate of f of n is less than or equal to the growth rate of g of n, that is what we said. It cannot be more than g of n. So, this g of n is called the upper bound of f of n. If you can see this, no faster than. So, this is the upper bound of f of n. So, let us take an example to simplify the running time of the estimation. After all, it is an estimation for a function f of n, we ignore the constants and the lower order terms. So, if you have 10 n cube plus 4 n squared minus 4 n plus 5, if you have found out that this is the T of n, okay, then we do not say everything, we just say it is of the order n cube, where n cubed is the largest term, and we ignore the rest of it, including the constants. We also ignore the constants associated with the largest term. So, this is what is called as the order of n squared, n cubed. So, there are different growth rate, 0 of the order of 1 which is constant, of the order of log 2 n which is logarithmic, of the order of n, which is a linear, that is the time increases linearly with respect to the size, input size of the problem. Similarly, you have this is the logarithmic, and this is the quadratic, this is the cubic, and this is the exponential. This is it grows too rapidly, okay, of the order of 2 to the power of n. As the problem size increases, the running time increases exponentially, or it grows very fast. So, these are some of the typical functions or big growth rate functions, and you can see that we would like it to be 1. We would like, that is almost impossible. We would like it to be, if you have an algorithm that is log n, it is the best that you can have. So, this is the way that they do it, the growth rate are defined. So, this is a comparison of the growth rate. So, suppose you take, this is the size, this is log n, this is n log n, and this you see for 10 it grows like this, but if you look here it grows very high. So, if you take like this, say 5 like this, you can see how it grows. So, this is what are we trying, as the input size of the problem increases, how is the running time increasing, how fast is the running time increasing. This is only an estimate, it is a rough estimate with a lot of assumptions. So, what are primitive operations that we can consider? Everything is considered as a primitive operation, evaluating an expression, assigning a value, indexing into an array, calling a method, returning from a method, all these are assumed to be primitive operations. Please note, we are assuming that it need not necessarily take that much amount. Now, let us take an example. This is calculating I cube. So, this is a sum, partial sum is initially equal to 0. For int equal to 1 to n, we are just multiplying the sum, and this is the problem. So, the cost of this is equal to the order of n. Why? You just do this n times. So, it is of the order of n. Now, if you take, so this is the first step, this is this takes 4n, this takes 2n plus 2, and this is 1. So, if you add all this, lines 1 and 4 costs 1 unit each. Line 3 is executed n times. So, it takes, each takes 4 units, and line 2, this is the initialization. Normally, for this part, the initialization, the increment, all that we take time. So, the approximate cost is, if you take like this, 6n plus 4. So, that is of the order of n. We are not bothered about the exact values. So, for loops, at most the running time of the statements inside the for loop is including tests, is the times the number of iterations, at least the number of iterations. So, suppose you have you are doing something inside a loop for 10 times, then 10 will be the minimum running time into. So, if you take nested loops, it will be of the order of n squared. Okay. So, if you do it like this. So, consecutive statements, you just add them. So, if you add of the order of n plus order of n square, is of, you take it as order of n squared, never more than the running time of the test plus the larger of the running times of S1 and S2. So, now you have what is called the best case, worst case, and average case. So, the maximum over the number of inputs, the minimum of the number of inputs, and the average. Normally, we try to find out the worst case. So, not all inputs of a given size take the same time to run. So, everything you have best case, worst case, and average case, you do not take the same. So, the sequential search for k in an array of n integers, you begin at the first element in array and look at each element in turn. So, if you have the best cases, you will find it at the first position, and then the cost is 1. Otherwise, you find it at the last position. The cost is n compares. Average time is n plus 2, that is the average time. So, you will always give the worst time. So, worst case is the longest running time for any input of size n, an upper bound, it is an upper bound. So, you are guaranteeing that the algorithm will finish and it will never take longer than that. So, sort a set of numbers in increasing order when it is actually given in decreasing order, that is the worst case. So, in searching a database for a particular piece of information, these are all worst case. So, normally we do the worst case. So, we know that this is the worst that can occur. Best case, sort a set of numbers in an increasing order, and the data is already in increasing order, that is the best case, you do not have to do any work. But the difficulty in average is the best, but the difficulty in average is you cannot determine what is average. So, next we come to a small topic which is called recursive algorithms, and here we have already discussed how to determine the running time of iterative algorithm. In order to do recursive algorithms, we require more sophisticated techniques, and that is using recurrence relations. We are just going to look at it in a small way. So, this is the factorial function, if you recall, n factorial. It takes time 1 if n is equal to 1, otherwise it takes time n into n minus 1. Takes time n in equal to n minus 1 if n is greater than 1. Consider the recursive algorithm. So, this is factorial, you are trying to find out factorial. What you have to note here is you are calling factorial n, in which you are using factorial n minus 1. So, this is a recursive algorithm. If n is equal to 1 or 0, you will come out. So, this is the analysis. Normally, you say when n is equal to 1, we do not perform any action, otherwise we perform 1 plus how many ever times you multiplication we perform to the recursive call f factorial n minus 1. So, this is the number of multiplications we will have to do. This is called the recurrence relation, and the time taken will be t of n equal to t of n minus 1 plus n. So, this recursive relations are used when algorithm contains recursive calls to itself. And so, what is the actual running time? For that we have to solve the recursive algorithm. We will take an example of an ordered array. So, you have L0, Li and mid. This is the algorithm. If it is greater than Hi, you return false, that means it cannot go beyond. Otherwise, you take the mid and you keep calling. If it is less than mid, you call mid minus 1 to x. If it is greater, you go mid plus 1 to x. So, this is how you do L0 to Hi. So, here you have the recurrence. T of 1 takes time 1, T of n takes 2n, because you are dividing the data into half, 2 t into n by 2 plus n, where 2 t n by 2 is the 2 sub problems, each of size n by 2, and this n is for patching the 2 solutions. So, you have here this, but this can be written as 4t plus n by 4 plus 2n, at by n plus 4 plus 3n and so on. So, approximately this is the 2 power k t n by 2 power k plus k n, and the running time of this particular algorithm, therefore, if you take log and solve it, is of the order of n log n. So, this is approximately n t of 1 plus n log n. So, it takes time of n log n, which is what we are trying to say for this particular problem. So, this is how the recursion problem is solved, using you first solve for n by solving for n minus 2, then you solve for n by 2 by solving for n by 4 and so on. So, what have we discussed in this algorithm analysis? We have discussed the analysis of algorithms and the need for such analysis. We understood the concept of time complexity and how it can be estimated, and we briefly, very briefly explained the use of recurrence equation for analyzing recursive algorithms, which we cannot do without recursive algorithms. Now, why did we talk about algorithms here? Because the algorithm, that the nature of how you define the algorithm is very much dependent upon the data structure you use, and so in a course on data structures we should know how it affects the algorithm running time, and that is why we spoke about data structures, algorithm analysis in this particular module. Thank you.